Great. So thanks for the invitation and the introduction. And so my goal here is to give you an overview of one of my favorite subjects, which is dark matter in our universe. And I gave it the title, which was a little bit of a reference to the Hitchhiker's Guide. But that's really where we're at. We're just sort of having the opportunity to look at the entire universe from the largest scales down to clusters of galaxies, galaxies into our solar system, and right here on the Earth to try to piece together this puzzle of what the dark matter is. Okay? So it's not really the Hitchhiker's Guide to the galaxy, it's actually the Hitchhiker's Guide to the universe. Okay. So let me step back and just give you kind of a big picture. Let me start a little bit philosophical. So when you look up at the night sky, so for example, here's our Milky Way. What you see, you're led to believe that the universe is dominated by stars. On the other hand, we also know that appearances can be deceiving. So it was also thought, several hundred years ago and through the centuries really, that the Earth was at the center of the universe. And the Ptolemaic universe required more and more complicated explanations as the observations got better and better to make a consistent picture of the universe. And of course, we all know what the outcome of that was, that once we were willing to drop that we were the center of the universe, that everything became very simple again. And that we were able to explain everything with one very simple law, Newton's law, and all the observations came through that one simple law. Okay? And so, so here now, today, this sort of trend has continued. Not only are we not at the center of our solar system, but we've also learned, as we've been able to look farther and farther along, as our understanding has gotten better and better, that we're not even at the center of our, I'm not supposed to use that, am I? Not even at the center of our galaxy. So here's the center of the Milky Way galaxy. The sun is sitting out here approximately 26,000 light years from the galactic center. We're whipping around the center of this at about 250 kilometers per second. And just to give you an idea of the scale, a light year is about 10 to the 16 meters. So it's an awfully long way. And if you just take one more step further, and I take that Milky Way galaxy, our galaxy now, and I tip it now on its side. So what we were looking down from top, now we're looking at from the edge. So the sun, again, is sitting out here far from the galactic center. What I want to point out to you is that, in fact, what we're doing is what we see is actually sitting in some large dark matter halo that actually engulfs the whole thing. Okay? And we don't see this in stars. And we're actually able to know, and I'm going to describe this in detail, that this is some alien form of matter. And when I say alien, I mean we don't have a theory to describe it. Now, what follows is that we're actually living in a fog of this alien matter, of dark matter. And you can compute, based on what we know, what the density of this alien matter is right here in this room. And we don't have an exact number of what it is, but we can estimate it. And we know that its density, now I'm going to convert these units for you. So I wrote it in particle physics units, 0.1 GeV per centimeter cubed. A proton is about 1 GeV. Okay, so it's about a tenth of a proton mass per centimeter cubed. Okay. Now, this is the density of dark matter here in this room. By contrast, we know that the density, for example, in electrons, something like 5 grams per centimeter cubed, or if you just convert that to our favorite units, it's up by about 25 orders of magnitude. So in this room, there is dark matter all around us, but its density is much, much, much smaller than what ordinary matter is. Okay? Now, the Earth is a very unusual place in our universe. Most of the universe, when we look out, is actually just empty space. There's nothing in it. When instead you sum the entire universe and you ask how much of it is ordinary matter, the number that you get is actually about 12% in atoms, 15% in photons, and 10% in neutrinos. So these are the particles that we understand. These are the particles that we have theories for, and the rest of it is in some exotic form of matter. Okay? And you can use any set of dramatic words that you like, but the scientific way to say this is that we simply don't have a theory to describe it. And what I mean by a theory is very detailed, microscopic, is the standard model. So we believe that the standard model actually describes the rest of this pie on the previous page, and the rest of it is just the 6 quarks that we know so well, the forces, and then the neutrinos and the leptons. Okay? And some fraction of these are stable and exist in our universe. Okay? And that describes this part of the pie. And it's, in many cases, verified to 1 part in a million. So precise, beautiful observations that verify this theory that we have, the standard model of particle physics. But all we have for dark matter is a big question mark. Effectively, what we do is to pick up our universe and weigh it. And I'm going to tell you how we do that. But we don't actually have any description of what this is, even though it's dominating the dynamics of our universe. So as you might imagine, this causes something of a paradigm shift. So similar to the Copernican revolution, okay, which went from Earth-centric to heliocentric, observations have really have forced this new viewpoint on us. And this new viewpoint is that the dynamics, the formation of structure, the way it evolves, is not dominated by ordinary matter. It's not dominated by the things that we have theories to describe. It's dominated by dark matter. But once we introduce this idea of dark matter, then all of the observations that we have, which I'm going to tell you about in more detail, can be accounted for completely. And it comes out very simply. Okay. So dark matter dominates our universe, but we can't see it with our eyes. And in order to accept this, you have to accept 2 claims that I'm going to tell you about. The first claim is that dark matter does in fact dominate the structure in our universe. So I'm going to start this talk telling you about the evidence for dark matter. The second claim is that you could ask, well, why isn't dark matter just happen to be ordinary matter that doesn't interact with the photon? Why doesn't it just happen to literally be, say, a dark atom? Why doesn't that work? And the second part of the claim is that it's not described by any of the theories that we know. Okay. So then the natural next question is, how do we identify what the nature of the dark matter is? Okay. So let me start with this first one. And let me first begin by clarifying something, which is to define what is it that I mean by our universe. What is our universe? Well, our universe is not that when I look out in space, somewhere space just ends. Okay, that's not what I mean by our universe. What I mean by our universe is the area of space that at one time was in causal contact with us. Okay. By that I mean we can see it. Okay, so we know by Einstein's theory of special relativity, what that means is it's the distance that light could have traveled in the entire age of our universe. Okay. And the age of our universe is something like 13.8 billion years old. So the size of our universe is 13.8 billion light years. Okay. And if you put that in, what you find is that's about 530,000 times the size of our galaxy, okay, which I already said was about 10 to the 17 meters from us to the center of the galaxy. So these are very large scales. But one of the remarkable things is that using cosmological tools, we can actually learn about things in great detail. So let me tell you about a couple ways that we can do that. Okay. So let's take our own galaxy. This is actually the place where we started. And let's see if we can just weigh it. So what are two ways that we can pick up a galaxy effectively and just weigh it? Well, there were two methods that astronomers used. The first one was to say, well, I can pick up a star here and I can actually measure its velocity. And we know that Newton's law relates velocity to enclosed mass. Okay? And so for all of these stars, I can just do this systematically. I can start at the center and I can work my way out and just make measurements systematically of the velocity of the stars from the center of the galaxy. So that's one method. The second method is I can just measure the amount of light that's coming from an area. And I believe I understand stars quite well. And in fact, I know how much light I get from stars, how much they emit. Okay? And so I can take the mass to light ratio of stars, and then I can multiply by the amount of light, and that gives a measurement of the mass. Now, if I believe Newton's law, and if I believe I understand stellar physics, both of these have been tested very well, then they should give the same answer. And they don't give the same answer. So that tells you that there's something in here that's missing. And in fact, you can measure this velocity as a function of the distance. This was done by many people over time. One person who was notable for it was Vera Rubin. And these are what you would infer just by looking at the stars. So if you, going away from the center of the galaxy, you can see that those measurements suggested that the velocity of the stars was falling off. And this is what the measurements, the actual measurements, said. So this is what you would infer from the light, and this is what you would infer from the velocity. It looks like Newton's law is in contradiction with what we know about stellar physics. So what's going on? Well, one thing that you can posit, and in fact they did posit in the early days when they first started seeing this, was that the way you make up for this is, well, all matter is just not in stars. It's just not visible, it's dark. And if I have a bunch of matter there that's dark, then I can make up this discrepancy from here to here and reconcile the measurements. Okay? Now these measurements date back even to the 30s. Okay? So people have observed this for a very long time, but you say, oh, maybe there's something I don't understand about stars. Maybe there's just a lot of dark, ordinary matter in the universe. Maybe there's something else I don't understand. There are big error bars here. This is what scientists do when they're confronted with a contradiction, is to start questioning the conclusion if it requires you to change your paradigm, which is what this would do. It's a paradigm-shifting thing. But time went on, and the measurements got better, and people found better ways to measure the amount of mass in our universe. So another way that you can use this is to use Einstein's theory of general relativity and the fact that gravity bends light. So if we're sitting here on Earth and there's some distant star, so forget about the details of this, but let's suppose there's some mass in between us and the distant star. What you can do is to look for the bending of the light around this mass here. Okay? So gravity actually bends light. And the reason that it does that is that it actually warps space-time itself. So in modern day, what does that look like? Well, there's this beautiful image of a pair of cluster of galaxies. Okay? And you'll notice, so here's a cluster of galaxies, and here's a cluster of galaxies. Okay? And the isocontours here on this plot show where the mass is. So this is inferred by looking at a distant source of light, some type of star, and then you look for the light to bend around the cluster of galaxies, and then you reconstruct what the mass distribution is using general relativity. And that's what gives you these two clusters of galaxies here. Okay? So this is just a measurement of the mass. It's not where the light is, just the mass. Okay? These colors here are where the gas is. This is where the visible matter is. This is where the ordinary matter is. And you can see that the ordinary matter is just not sitting where the bulk of the matter is. Okay? And what's actually happened here is that these two clusters of galaxies pass through each other. The ordinary matter, which interacts, was stripped off. This is called the bullet cluster. You can see the way that it was stripped off. And the part of it that was not interacting just continued to pass through. And that's the part of it that is dark matter. So this is another piece of evidence. We have more evidence. One is that we're actually able to look at the universe in its infancy. So last week, as I understand, there was a talk on the cosmic microwave background. And the remarkable thing about the cosmic microwave background is that it's a photo of the universe in its infancy. It actually tells us about the perturbations, about the small density perturbations when the universe was just 370,000 years old. So this is from the Planck satellite. And these different colors, so they're amplified. They're actually 1 part in 100,000 perturbations. So there's small, small fluctuations in this cosmic microwave background. And these are highly, highly significant because these little perturbations, you see little hot spots and little cold spots forming already. As the universe gets older and older, gravity starts to pull those overdensities. It tends to accentuate them. And the underdensities become even more underdense. And you can actually simulate this in detail. You can just take this map, put it on a computer, and then just use literally Newton's law to evolve this forward in time. And that's what has been done. So here is some work done by the Millennium simulation. And what I want to point out, let's just pick out one of these. So if you go back, you can kind of see the resemblance between these little perturbations here and what we see in this top panel here. So this is fast forwarded through about 1 billion years of evolution, and you can see that these little perturbations have grown a little bit. So now you can start the simulation and watch it evolve as time goes on. And as you go from one panel to the next, as you go down, so this is later and later time, you can start to see those densities, overdensities, grow. And that's just the work of gravity pulling things together and making the overdensities even more overdense and making the underdense regions even less dense. Okay? Now, you can make this highly quantitative and compare these simulations against what you see today. And there are sky surveys. So this is from the Sloan Digital Sky Survey, where you look up on the sky and you quite literally just count galaxies. You just look as far back as you can, go as far away from you as you can, and you just try to count how many galaxies you see. And then you compare this simulation to, this observation. See, this is how good it is. You can compare this observation against your simulation. And it allows you to tell you how much of this matter, dark matter, there must be in the universe. And so all these things put together give a very coherent, consistent picture. You can throw away any one or two, or really 3 of these observations, and they all tell you precisely the same thing. And the reason why it's so powerful is because you're doing this at so many different epochs. There are different systematics in these measurements. You're making different assumptions. And what you like to see coming out of your picture is that it all agrees. If your theory is working, if the need for dark matter is real, it had all better fall together. And it does, beautifully. So where does this leave us? Well, everything that I've told you so far is really about weighing dark matter. So everything that we've learned, when I say we weigh dark matter, what I mean is Newton's law works. I can just take mass and just see. It's very complicated. It's numerically very intense, requires very advanced techniques to do this. But the underlying physics is very simple in the sense that I really am just seeing how the universe evolves under the influence of gravity and taking this additional component of matter called dark matter. Okay, and so the conclusion is that we can weigh dark matter, and we know what its weight is. But of course, that's not a theory. It would be as if we didn't know about Standard Model or any of the other things that all of science really, and we just said, okay, forget our theory, we're just going to pick up the Earth and weigh it. And that's all we know about it is its weight. That's really where we are with dark matter. So what else would we like to know about it? Well, we would like to know the masses involved. We would like to know what kinds of interactions it has. We already know that it's not with the photon, so we're able to say what it doesn't interact in many cases. We know that it doesn't interact doesn't interact with the gluon. We'd like to know, is the dark matter sector simple or is it complex? Is it just one type of dark matter particle? Are there forces? Do they form into atoms, or is it just an elementary particle? In short, this is everything that we demand from a theory of dark matter. Okay? And so really what we're sort of entering into is this deep unknown, okay, where we're trying to probe this to get some more information about what might be there. Okay. So why is it so hard? You know, as I alluded to before, we've been thinking about dark matter since the 30s. Why is this problem so hard? And after all, there's dark matter. I started out this talk by saying that there's dark matter in this room. Why is it so hard to find it? Well, the reason is that its interactions with us are very, very weak. Okay? By contrast, you know, the things that, you know, this interaction, you know, is mostly through photons, through light. Everything that we've learned about the dark matter is really through its aggregate properties. So the point is that it interacts gravitationally. Gravity is really, really weak. But if I look cosmologically, these objects, a cluster of galaxies, is really, really heavy. So this object here, where I looked at it and looked for the light to bend around it, is about 10 to the 14 solar mass. Okay, so I can see the aggregate properties of the dark matter on really, really big scales. But if I want to learn something about the microscopic properties, that's just a much harder problem, and that's the one that we're really focusing on cracking. So then you might say, well, is this just fairy tale science? And we have, I can think of many examples, but here's a really good one, which is neutrinos. So neutrinos. The sun produces copious amounts of them. So the sun is a fusion reactor, and in this process, it produces neutrinos, lots of them. We have about 65 billion neutrinos from the sun pass through each square centimeter per second. So there are tons and tons of neutrinos that are right here in this room, flowing through us all the time. And yet it was really, really hard to detect them. And in fact, we had to go to rather heroic efforts to detect them. For example, there is this detector, Super Kamiokande. It's made of ultra pure water, and there are photodetectors. And what you do is wait for a neutrino to come through and have a very rare interaction, and then you look for the light emitted from the interaction. So we have an example. Why was it so hard to find these? And I want to give you an analogy. And the analogy that I want to give you is of mountain peaks. So schematically, if I make this x-axis inaccessibility, and I make the y-axis energy, okay? So us, the ordinary universe, you can think of this as being protons, electrons, photons, ordinary matter. It's pretty low energy. It's in the ground state of the system. And it's obviously highly accessible to us because this is what we do experiments in all the time. And the dark matter sector is sitting over here. And we don't know what the masses of the particles are. We do know that it's highly inaccessible to us. And you might say, well, why is it so inaccessible to us? Well, you can just think that between us and this other sector, there's some type of a barrier. Now, in the case of neutrinos, the barrier was the weak interactions, okay? So named because their interaction rate with us is relatively weak. Now, we don't know what the strength of the interactions of the dark matter with us are. We have some theories that give us some very good ideas of what it might be. But essentially what we're trying to do is to scale these peaks. And once we scale the peaks, the idea is that we get to the top, we're able to look over, and then we're able to start seeing what is the structure in the dark matter sector. Okay? And the analog here is of a hidden valley. You work, you hike, you keep going up, and eventually the other side opens up, and you start being able to understand what the nature of the dark matter is. So how is it then in practice that we actually go and detect dark matter? Well, as I alluded to before, what we're really looking for is really rare types of interactions. And there are effectively 3 ways you can do this. You can have 3 ways, well, there are more than 3 ways, okay? But I'm going to talk about the 3 dominant ways that we've been probing and ways that we're looking to extend this. Okay? So first of all, we have lots and lots of nuclei. Okay? And if you're sufficiently good at understanding interactions with nucleons, you might be able to see a really rare dark matter scattering. So that's the first way. It's called direct detection. The second way is that we have lots of dark matter in our universe. It's not particularly abundant here, but we know it's really abundant in the center of our galaxy. It actually spikes in the center of our galaxy. So you can put up a satellite and just point it at the galactic center. And you can look for very rare dark matter interactions there that produce things we can see. Okay? So that's the second one. I'll talk about that in more detail as well. So the first kind is we're just looking for rare processes. The third thing you can do is just to say, well, I'm just going to go straight up the top of the mountain. And you go straight up the top of a mountain by really producing the dark matter at a high energy in a collider like the Large Hadron Collider. So I'm going to talk about all these 3 ways of looking for dark matter. Okay, so the first one is rare scattering of dark matter. Okay. So if you're looking for rare events, you had better have quiet detectors in the sense that you want to make sure that all the other things that happen don't mimic your dark matter signal. So how do you do that? Well, one of the things that we're really worried about is backgrounds from cosmic rays. So these are really high energy protons that are produced from astrophysical objects, and they come crashing into the Earth's atmosphere. And when they do that, they produce energetic particles. Okay? And they come streaming down on us. This is your primary source of radiation when you take an airplane ride, is the energetic particles from these interactions. So you want to shield yourself from them. The same thing that gives you radiation in an airplane ride. And how do you do it? Well, you go into a mine. You go deep underground in some godforsaken place like Sudan, Minnesota. I shouldn't say that because I'm from Minnesota. It's actually beautiful. Okay. But you can go underground, deep underground. These are active mines in many cases. And you can build an ultra-pure, ultra-clean laboratory underground. Okay, so you want to try to minimize any effects from contamination. So you really need a radio-pure and a cryogenic detector. Okay. And so we've gotten very good at radio-pure and cryogenic detectors. So for example, this is an image from the CDMS experiment that was running in Sudan for many years. And the idea here is they have these semiconductors, so a germanium or silicon crystal. They have a dark matter particle. In this case, it's called a weakly interacting massive particle. It comes in, it deposits some energy in your detector, and then you're able to measure some of that energy in the detector. Okay. So that's the first way. The second way I said was that you look for rare dark matter interactions in our galaxy. So the idea is that dark matter comes in, and there's some interaction, and it produces particles we can see. And those particles propagate out, and eventually they appear as particles that are known to us and whose interactions we're very good at measuring. So where do you want to look? As I said before, you want to look for it where there's the most dark matter. And here is an image from a dark matter simulation. And that dark matter simulation, the color, shows you the density of dark matter. So you could take this to be the Milky Way galaxy. You can see it becomes really, really bright in towards the galactic center. And that's just because dark matter is heavy, and it tends to sink. It's very cold and heavy, and it just tends to sink, and it becomes very concentrated in the center of the galaxy. And so because there's a very high density of it there, you can look for dark matter annihilations there. Okay. So how do you do that? Well, you put up a satellite. So this is where, for example, the Fermi telescope, which measures high energy photons. And what do dark matter annihilations look like in gamma rays? Okay, so if I have dark matter particle in the galactic center, it annihilates, and it produces, at the end of it, say, very high energy photons. What does that look like? Well, the answer is that it looks like a feature. Okay, so here's an example of one. So here's the number of photons, effectively, is what's on the y-axis as a function of the photon energy. And you can see that this feature here is one that potentially would be correlated with dark matter. Okay, and you can see that it's rising above the background. No, there were not, well, there are no error bars on this. And in fact, one of the challenges is understanding your systematics well enough to be able to say confidently that you have a signal. This was one potential signal that people considered for some time as being due to dark matter. And it turned out that when Fermi looked at this more carefully and reanalyzed their data, that they found that this was taken away. Okay. So this field is very exciting. We get potential hints for dark matter, and then we look more closely, and then we find so far that none of those have held up. However, there are still some of these that we're looking at intently. So this is one that people have been studying intently for the last several years. So this is a picture of the galactic center with the backgrounds subtracted, what we understand to be the backgrounds. And you can see that there's an excess here. Its profile, falling away from the galactic center, is consistent with what we would expect from dark matter. You can see that its morphology is spherical, which is significant because if you recall, when we looked at our galaxy, it's very pancake-like. So you would expect, if it were due to ordinary matter, that it might look more pancake-like, but this looks very spherical. And the energy distribution is consistent with what you might get from dark matter annihilating, in this case, to B quarks. Okay.
What's the scale of that picture? Is it degree thick marks, or what is it?
So this plot goes from plus 90 to minus 90. So the size of this, degrees, correct. So this is very extended. This is a few degree extended excess towards the galactic center. Okay, so it's big. It's there. Whatever this is, there's some type of an excess there towards the galactic center. We're not exactly sure. We're not convinced that scientists are skeptical. Okay, and
this is like a picture of half the sky. That's what you're showing.
Yes. Mm-hmm. Exactly. So if I just, yep. So
Could you
a black hole instead of due to dark matter? How can
So-
you rule that out?
So one thing that people are, in fact, concerned about is that we haven't characterized adequately the astrophysical backgrounds in the galactic center, including from, for example, the black hole, which is much, much smaller extent. It, on this picture, would just be a point. Okay? So in order to get these gamma rays from the black hole, if it were to come from there, you would somehow have to get the particles to propagate out in this spherical way and to produce gamma rays with the spectrum that we observe. And people haven't focused on black holes. They've focused on millisecond pulsars as the background that might explain this. It turns out that this is actually too bright and doesn't have exactly the morphological features that you might expect from a pulsar signal. So that's one thing that people have talked about, but we haven't really gotten a good model that might be able to generate this. Okay? So that's absolutely the right question to be asking, is what else could do this? Galactic center is complicated. What else could do this? We haven't. People have been shooting at it, coming up with various different models that could explain this, and we haven't come up with one that is satisfactory yet. Of course, we're still looking. Any other questions? Yes. Yes.
What are these high energies? What energies we are talking about of those photons?
So these here are in the few GeV range. Okay, so they're not super high energy, but they're still gamma ray energies. Yes? Yes, and well, people have tried that. They've tried modifying gravity, and it's really hard to modify it and to explain all the observations from the cosmic microwave background to the formation of structure, to what we see in galaxies, to things like the bullet cluster, just by modifying gravity. And you tend to have to work really hard. The theory tends to become sick. And so people have certainly tried that, but so far have not found a successful way of explaining all of the theories. Okay, sorry, all the observations. Okay, the opposite. By contrast, dark matter does all of this with just one parameter, which is a density. Okay, so we tend to accept solutions that explain the data with the least amount of, it's like the Copernican universe, right? So you can put in the epicycles, and you can put in arbitrarily many, and you can even fit the data by doing that. But by contrast, once you accepted that the Earth went around the sun, it only required Newton's law, and that was it. It's really the same thing. Okay? People have tried to put in epicycles to modify gravity, and it hasn't. It breaks. It always breaks.
You called it annihilation, but is the particle-antiparticle annihilation, or is it like the quark-quark and the thermal energy is what's driving conversion?
So it will depend on the theory of dark matter. So in some of the most popular theories of dark matter, the dark matter is its own antiparticle. And so it can self-annihilate, which is actually different than in the standard model, where particle-antiparticle annihilates. But there are other theories of dark matter where you have particle-antiparticle. And so there again, it's particle-antiparticle. So if we knew more about the theory of dark matter, or really if we knew anything, then we might be able to answer that.
So if I might suggest, depending on how you want to structure the talk, maybe we can let the speaker carry on for a little bit unless there's essential questions for clarification and reserve some more discussion for the end of the talk. Is that?
Sure. Okay. So we can look for dark matter annihilation that produces high energy photons. We can also look for dark matter annihilation that produces charged particles. Now, one difference between photons and charged particles is that the charged particles are charged. And there's a magnetic field in our galaxy. And the fact that there's a magnetic field and that there are other photons around, that means that when I produce a particle that has annihilated somewhere, it doesn't come straight to us. When I produce a high-energy photon, it just comes straight to us, and I just look towards the galactic center. A charged particle random walks its way through the galaxy, and that's what's meant by these wiggles here, and eventually it reaches us, and so we don't actually get any directional information because it's been randomized by the time it reaches us. However, randomized information doesn't mean no information. There's this alpha magnetic spectrometer that's currently on the International Space Station. And the idea of this is basically as a giant calorimeter. It's essentially meant to measure the energies of charged particles. And so what would dark matter look like? Well, again, you don't get directional information, so you don't get to look towards the galactic center. But again, here you look for a feature. So here's an example of what you might see. If dark matter with some mass would annihilate to charged particles, and you can see that you look for some type of a feature which is at the dark matter mass itself. So that concludes the second way to look for dark matter. Then the third way, as I said, was to just go and scale the mountain. So coming back to this picture of the hidden valley with us and the dark matter, I said, well, you can just scale the mountain and then just take a look over and see what's in the dark matter sector. And this whole thing of scaling the mountain means going to higher and higher energy. And high energy colliders, depending on the theory, can in fact produce dark matter. And I'm sure as many of you know, the energy in the beam of the Large Hadron Collider is rather impressive. So this was an image from CERN. So you can see the Alps up above. And this is an aerial view. This is the ring of the Large Hadron Collider with this tunnel going through it. And the reason that you need that is so that you can first accelerate and then bend particles as you're accelerating them. You need a very large ring in order to do that. And we've been very excited by the results that we got out of this. Okay? Even Google paid a tribute to the start of the LHC. And we've really, these are impressive, really impressive detectors. So the idea here is that these beams of protons, very energetic protons, come in and they smash together. And when you smash together in that interaction, you can potentially produce a dark matter particle. And so these instrumented detectors are actually meant to look for the byproducts of that collision, which are spectacular. And so here is the interaction point of the proton on the proton. And here you can see a few, these are called jets for reasons that are probably clear. And as you probably also heard, there was the discovery of the Higgs, so in this detector. So now before that photo was this side of this detector looking on it. So here's a rendering of the detector. They're very long as well. Here's the collision point again. And this is actually a Higgs event. So what this shows, you can see that there's particles here and here and particles down the end caps. This is actually the Higgs to 2 Z bosons. And then you can see the 2 muons and the 2 electrons coming out of this event. Okay. So what is it that this has to do with the dark matter? Well, it might have everything to do with it in the sense that the Higgs may in fact be one of these peaks. Okay? And it can actually, in many of these theories, in fact, it does mediate dark matter interactions with us. And so the idea is that when you produce these states here, it might be the Higgs alone. It might be the Higgs plus other things. When you produce these states here, that you can produce, as a byproduct, really, dark matter. Okay? So what does dark matter look like in one of these detectors? Anyone have a guess? And no physicists, please. Doesn't look like anything, exactly. It doesn't look like anything. However, energy and momentum is still conserved. And we can use that information. So now looking again down the detector. So the idea is that I might have an event. I have some, say, jets. I have some leptons. And the point is that dark matter doesn't look like anything. But nothing looks like something, because we know that energy and momentum is conserved. And so if you have a lot of something and then some nothing, that's called missing energy. And you can characterize that very precisely and use it to look for dark matter.
Is that just the cartoon, or is that the actual distribution that they see? If you look the longitudinally in the machine.
This is a cartoon. They see missing energy all the time because dark matter is not the only thing that can produce missing energy. The Standard Model does it too because there are neutrinos. And so they see these types of events all the time where they have a mismatch between the energy that they see and the energy that they don't see. And so they can actually use that to test the Standard Model electroweak interactions. And so what you actually have to do is a little bit more complicated than what I said. You don't just have to look for missing energy. You have to look for missing energy that's not characterized by Standard Model interactions. And so what you're doing again, and always what you're doing at the LHC, is to look for an excess over your background. Fortunately, the Standard Model is an extremely precise tool, and this is where the theorists come in, is we make predictions. And then what they do is try to look for an excess over the predictions. And so far, everything has matched up very well. Okay. Now, if there is an excess over the prediction, then of course you don't believe it right away. What you do is to say, you try to look for other ways, then the theory comes back in again because the theory will tell you, well, if it looked like that in this particular type of collision, then there are other signatures that go with it. So let's try and look for those. So you're always looking for many faces of one coin. And the theory is always telling you what those faces should look like. What are the correlations? You're always trying to piece these different parts of the puzzle together. And so you have to have the theory to do that. Okay, so all methods of dark matter detection are really different faces of the same coin. So I said there were these 3 different ways to look for dark matter. Well, at the end of the day, what we're really doing is looking for dark matter interaction with ordinary particles. And I said there were 3 ways of doing that. You can look for it directly underground. So dark matter interacting with the Standard Model, it can come in. So let's say this is a nucleon. It comes in, it scatters off the nucleon, it comes out, and then you look for the recoiling nucleon. That's one side of the coin. The second side of the coin is that you look for dark matter annihilating to the Standard Model particles. So the photons, the gamma rays, are the things that we talked about. That's the second part of the coin. The third side of the coin is that you produce it. So you have proton-proton, say in the case of the LHC, and you hope that you can produce dark matter on the other side of it. Now, I've said all of this, that dark matter is really an exciting field. And I want to close the talk part of this by just saying why I think now is a critical moment. And the reason is that we've had good theories of dark matter for about 30 years now. And we've been looking for intently kind of 2 theories of dark matter. I'm going to talk about one of them. And where we're at right now is we're not going to totally eliminate these theories, but we're really closing, so we just have a little sliver of the parameter space left. And the theories are starting to look like, we don't think that that's it. And so we have to move on and think about other things. We need to have the theory to tell us where to look. But so far, we haven't hit the nail on the head. So let me tell you what that dominant paradigm is. The dominant paradigm, okay, is being tested, okay, not ruled out yet, but on the timescale of the next 5 to 10 years, it's going to be at the point where it's really going to be very, very strongly tested. And that paradigm is the weakly interacting massive particle. And the idea of this is that it's called weakly interacting because the dark matter interacts with us through the weak interactions, or actually what we're testing right now is interactions with us through the Higgs boson. That's what we're focusing on right now. And it's actually even more narrow than that. people have been really focused on supersymmetry. Supersymmetry is a beautiful theory in the sense that dark matter comes out of it for free, and it explains some theoretical puzzles in the Standard Model. But what comes out of supersymmetry is a lot of extra particles. In fact, every single particle in the Standard Model has a superpartner, every single one of them, and they get ridiculous names. So the partners of the quarks are called squarks. The partners of the leptons are called sleptons. The partners of these are called enos. So this is a xeno, a weno, a photino, and a gluino. And the partner of the Higgs is called the Higgsino. Okay? We say these things with straight faces, really. Okay. And one of the reasons that this theory is so important is, first of all, it solves theoretical problems within the Standard Model itself. So it does something independent of the dark matter. And the second reason, I think, is really that it's highly predictive. So in the sense that the Standard Model interactions we know very well. And I've just told you that I've effectively doubled the Standard Model. Now in doing that, I've introduced some free parameters. But I know quite a bit about Standard Model interactions. And because I do, it actually tells me about how the Standard Model interacts with the dark matter. And so I can make predictions. So let me just talk to you a bit about what those predictions are. And this is going to get to be slightly more technical. So let's talk about the first one, direct detection. So this is a plot. This has interaction strength as a function of dark matter mass. There's an immense amount of detail on this. Let me just point out a few relevant things. So first of all, the solid lines here are things that are currently ruled out by experiments. Okay. So the solid lines means you've built the experiment, you've done it, you didn't find anything, so you've ruled out some dark matter mass and some interaction strength. So anything above a solid line, so for example here, is ruled out. The dashed lines are projections. So in fact, experiments that are approved and currently being built, so for example, xenon 1 ton and LUX are both experiments. Well, so LUX has results already. Xenon 1 ton is in the process of also being built. And then the next generation after that, which is going through R&D, is called LZ. And you can see that this is going to push through. Notice that this is a log plot. So these are ordered factors of 10. Factors of 10. Each one of these dots is factors of 10. So you're just gaining a factor of 10 in interaction strength for each one of these. So this is a lot of gain. This red blob here is the prediction of the theory. Now, we're going to be here on the 5-year time scale. Okay? We're talking about the next generation after that. And once you get down to here, you hit what's known as the neutrino floor. It just gets really hard to do that experimentally. Fortunately, by the time you get there, you've already ruled out most of the theory. Okay? And I should comment that this is the region where dark matter is interacting with us through the Higgs boson. Okay? So it's a particle that we've discovered. And this theory predicts that dark matter is going to interact with us through the Higgs boson. So we're going to just march down and just kill most of this region, or observe it. Okay? In which case, there will be a lot of work to characterize it. Okay? So that's the first side of this. The second side of this is dark matter annihilation to Standard Model. Okay? So what's going on there? Well, here again, on the vertical axis, this is interaction strength. This is basically an annihilation rate. Okay, the larger this is, the more photons you get from the galactic center. The union of this blue line with the yellow band is a prediction of one of these classes of models. And this blue line here is actually what's currently ruled out by an observation. And you can see that there's already a tension between this particular class of models and what the constraint is from the observations. Now, this isn't the only theory. There are other theories, but those are also getting stretched. The last side of this is the production at colliders. These LHC experiments are amazing in the sense that they're large collaborations, and they really systematically go through many different channels looking for the dark matter. And I don't expect you to take anything in detail from this list. What I want to tell you is you just look at all the different channels that they're looking at. And most of these have dark matter in them. And this is the mass, and this is what they're ruling out. So they're systematically working through all these different channels, looking for dark matter to appear. They haven't found an excess yet. The next run of the LHC is going to be starting soon. And so we're going to keep piling through this parameter space. Okay. So where are we at? Well, game is far from over. So we have this enormous puzzle. We know from so many different pieces of evidence that dark matter exists, that it dominates the dynamics in the universe. We know that it has to be some new type of theory, and yet we don't yet know what that theory is. We have some good ideas. We've been probing those ideas. We're pushing down through the parameter space. We may detect it in the next 5 to 10 years, but we may not. Okay? So what do? You can stop. You can throw up your hands and say, gee, the first thing I tried didn't work. Game over. Of course, that's not what you're going to do. You're going to keep writing and working and thinking, most importantly thinking, about how it is that we can probe the dark matter sector, because this is one of the biggest puzzles out there, is what is this stuff that's dominating the dynamics of the universe? Now, it may be, we don't know yet, that our first best idea was the right one. Dark matter might be discovered, in which case you will definitely hear about it. Okay? But it might not be. Okay? Our first best idea, or even classes of ideas, may not. And then in that case, we're really back to the drawing board. Now, we've already gone back to the drawing board, really. We've been thinking and working. And we have ideas for new detection techniques that are ongoing, they're moving, but if this is not actually discovered, those efforts are going to be really redoubled, or I think actually more than that. Okay. So where do you go? Well, as you can start to see, while we're probing really well this parameter space where the dark matter is, say, heavier than 10 times the proton mass. But, there's a great universe. Okay? So for theoretical reasons, we think that elementary particles are probably not the dark matter much above this scale. However, there's a great distance down here. So for example, the proton mass is down here, and we currently do not, you see there are no solid lines there. There are currently no constraints there. You might say, well, is that just because there are no theories there? And the answer to that is no. There are even very, very simple theories that live there. So one example is what's called asymmetric dark matter. And asymmetric dark matter is motivated by an extremely simple observation. And the extremely simple observation is that if I just look at the density of ordinary matter to dark matter, that ratio is about a factor of 5. Why is it a factor of 5? It could have been anything in principle. Why is it a factor of 5? Well, it could just be an accident. It could be anthropically tuned such that we could exist, or there might be a dynamical reason for it. You might relate the two. Well, what do you predict? Well, you find when you work through this that the dark matter mass turns out to be about, now there are order 1 factors, or even more than that, 5 times the proton mass. Proton mass is 1 GeV. That puts you in the 5 GeV range. 5 GeV is right here. You see all these constraints are dying just above where you might be sensitive to this. So even not having worked very hard, just looking at taking the next step and taking an observation, you find that you actually get very good theories that are currently not in the range of what is detectable. Now, this idea came along on the order of 5 to 7 years ago, and people started working. And the result of that was that people designed experiments. And so now you can see that we're to the point now, no experiment has been built yet. It's been designed, it's in R&D phase right now. And you can see that for these theories here, that there is an experiment now that's going to be built over the next 5 years that's going to be able to test certain of these classes of theories. However, we're going to go through that. Maybe we'll discover dark matter, but maybe we won't. So we have to keep looking. And so now we've started expanding our thinking and seeing, well, there's all this parameter space down here. What kinds of theories live down there, and what might be their signature in these types of experiments? Okay. So now we're actually actively working on designing experiments that are going to be able to probe this part of parameter space as well. And we're thinking about what kinds of theories of dark matter reside there as well. Okay. Now, I just want to, before I close, just give you a bigger picture that what's really happened in dark matter physics over the last 5, 6, 7, 8 years is that our thinking has shifted. So before, we were really focused on a couple of theories. They're very well-motivated theories. They may, in fact, be the right theories. We're still looking for those. But our thinking has shifted. So you recall before that we had the Standard Model. We had the dark matter sector. We know that the Standard Model has lots of dynamics in it. Okay? The Standard Model has these quarks and the leptons and 3 forces plus gravity. But we thought that the dark matter sector was simple. It was just one particle, one stable particle, plus other things that decayed to it. Well, it may just be that whatever's over here is much more complicated, that there might be multiple states, and that when we get up to these peaks, that what we might find on the other side is much more complicated. And so what's really required for this cosmic problem is multifaceted probes. And this is one of the things that I love about working in this field, is that you have the opportunity to look up in the sky from the time that the universe was 370,000 years old to clusters of galaxies in our universe, to underground and direct detection experiments, to large-scale surveys of galaxies towards the galactic center, and then also at the LHC. And all these different parts of the puzzle are helping us to tell us what we might find to solve this puzzle about what it is that's dominating the matter in our universe. So I'll stop there.